Imagine this, a gigantic dam in China so massive, containing billions upon billions of liters of water, that it could actually slow down the rotation of the Earth. Sounds unbelievable, right? The headline almost feels like clickbait. But let's use this as an opportunity for a fascinating physics lesson that will completely change how you see rotation and movement. By the end, you'll understand not only whether this claim is true or false, but also why it connects to everyday things, from how your phone knows its orientation to why a spinning skater speeds up by pulling in their arms. Here's the spoiler up front. Is it correct that such a dam could slow down the Earth's rotation? Yes, but not really. Technically yes, but in practice, the effect is so minuscule that it's practically irrelevant. Still, the physics behind it are mind-blowing, so let's dive deep into one of the most fascinating areas of mechanics: the physics of rigid bodies. This field studies solid objects that don't deform as they move or rotate, like a spinning top, a rolling ball, or even our own planet. To understand this properly, we need to upgrade from the basic physics most people learn in school, things like projectiles and point masses, to a richer picture that includes rotation. In basic mechanics, we simplify everything by treating objects as points. For example, when solving projectile problems, we ignore air resistance, assume a perfectly uniform Earth, and treat the projectile as a single point. This simplification makes the math easier, but it also hides the rotational behavior of real objects. Physicists make these approximations because they work surprisingly well as a first step. Once we understand the simplified version, we can add complexity step by step. It's the same reason there's an old physics joke about the spherical cow, where a physicist simplifies a cow into a sphere to make calculations easier. Real objects, however, are extended bodies. A train, a plane, or a ball has size, shape, and mass distribution, which all matter when we study rotation. So what exactly is a rigid body? As the name suggests, it's a solid object that doesn't deform while moving. Every point in the object maintains the same relative position to the others. Examples are everywhere. A book, a dumbbell, a coin, or even Earth itself. Our planet can be treated as a rigid body when analyzing its rotation. Before we fully jump into rigid body dynamics, let's recall some basics of linear motion. The key quantities are position, velocity, change in position over time, and acceleration, change in velocity over time. Above all, the most important quantity in linear motion is linear momentum, which is mass times velocity. Momentum is fundamental because it is conserved in isolated systems. This is the underlying principle behind Newton's three laws, which can all be expressed in terms of momentum conservation. When two billiard balls collide, for instance, the total momentum before and after the collision is the same. Conservation laws like this are the backbone of physics because they allow us to predict outcomes in complex systems. For linear motion, the queen quantity is momentum. But what about rotation? To analyze rotating systems, we introduce new but parallel concepts. Instead of position, we use angular position, the angle relative to an axis. Instead of linear velocity, we use angular velocity, how fast that angle changes. And instead of linear acceleration, we have angular acceleration. And just like linear motion has linear momentum, rotational motion has angular momentum. Angular momentum plays the same fundamental role. It is conserved unless acted upon by an external torque. Torque is the rotational equivalent of force. It's what changes angular momentum. Angular momentum depends on three things: mass, velocity, and how far that mass is from the axis of rotation. This is where the concept of moment of inertia comes in. The moment of inertia is the rotational analog of mass. However, unlike mass, which is constant for an object, the moment of inertia can change depending on how the mass is distributed relative to the axis of rotation. Think of a figure skater. When the skater pulls in their arms, their mass doesn't change, but the distribution of that mass relative to the axis does. By decreasing their moment of inertia, they spin faster to conserve angular momentum. Similarly, if they extend their arms outward, the moment of inertia increases, and their spin slows down. Now let's connect this to Earth. Our planet rotates around its axis with a certain angular momentum. The Earth's angular momentum depends on both its angular velocity, how fast it spins, and its moment of inertia, how its mass is distributed. If you take water from lower elevations and store it in a massive reservoir at higher elevation, you are effectively increasing the average distance of some mass from Earth's axis. That means the Earth's overall moment of inertia increases. Because angular momentum must be conserved, an increase in the Earth's moment of inertia would cause a slight decrease in its angular velocity. In other words, the Earth would spin just a tiny bit slower. Here's where things get interesting. Theoretically, yes, a huge dam could cause the Earth to rotate more slowly. But practically, the effect is ridiculously tiny. The mass of water in even the largest reservoir is insignificant compared to the total mass of Earth. Even though the physics is real, the change is so small that it would be impossible to measure in any meaningful way. This concept applies to everything. Whenever you climb a mountain, lift an object, or even move a bottle of water to a table, you slightly change Earth's moment of inertia. But the change is so incredibly small that it doesn't matter. Headlines about the Earth slowing down because of a dam are technically correct, but extremely misleading without context. Before we continue, if you're enjoying this deep dive into physics, make sure to like this video and subscribe to the channel. We post fascinating science content every week, and your support helps us create even more videos like this one. Back to our lesson. Angular momentum conservation explains much more than dams or spinning skaters. It's the same principle that governs how stars rotate. When a massive cloud of gas collapses under gravity to form a star, its size shrinks dramatically. Because angular momentum is conserved, as the cloud contracts, it spins faster. Neutron stars, some of the densest objects in the universe, are extreme examples of this, spinning at incredible speeds because their size is so small relative to their mass. The principle also explains why gyroscopes work. Your phone, for example, has tiny gyroscopic sensors that detect its orientation, letting it know whether it's vertical or horizontal. Satellites also use gyroscopes to maintain orientation in space. Even riding a bicycle relies on angular momentum. Once you're moving, the rotating wheels help stabilize you and keep you upright. So, coming back to our original question, does building a gigantic dam in China slow down the Earth's rotation? The answer is yes, but the effect is so absurdly small that it's meaningless. The amount of water is negligible compared to the Earth's total mass, and the change in distribution barely affects the planet's moment of inertia. While the physics is correct, the practical impact is zero. Understanding this example is a great reminder of both the power of physics and our own insignificance compared to our planet. Every tiny change we make technically has an effect, but in the grand scheme of things, Earth barely notices. Thanks for watching. If you enjoyed this video, don't forget to subscribe and explore the channel for more fascinating explanations of the universe around us. We upload new videos every week, so stay tuned for more amazing science content. See you in the next one!